In this video, we're going to see what are don't care combinations or simply don't cares in digital logic design. To start with, let us consider a function f of xyz. Okay, it's a function of three variables, and usually if you look at function definition, it usually will be like for some input combinations the function will be having output 0, and for the rest of the input combinations the output of the function will be 1. Okay, and we usually cover all the possible input combinations for that function. Okay, the function will have either 0 or 1 as the output, right? And there is a proper mapping from possible input combinations to the output. Now this is a normal scenario. So now suppose say we have function definition in such a way that, okay, suppose say g of x y z, okay, and for some input combinations output is 0, and for some input combinations output is 1. And if there are some input combinations for which the designer doesn't care what the output of this function is, those particular input combinations are known as don't care combinations, and the output of this function is don't care, and you don't worry what the output of the function should be for those don't care input combinations. Okay, so now how do we use those particular input combinations? We'll see them in this video. And now a question arises, why do we have some input combinations for which the function's output doesn't matter at all? To understand that better, we'll consider an example to illustrate why we should take them as don't cares, or the function's output is a don't care. Okay, we don't care about the output of that function for those particular input combinations. Okay, now to start with, we will take a BCD to XS3 converter, okay, to take it as an example. So now we have a decimal numbers which are represented from 0 to 9, and their corresponding BCD numbers, how they look are like for 0 0 0 0 0, and similarly till 9 it has been written out here. So this is called BCD because the decimal numbers are coded into binary, which we call it as binary coded decimal. Okay, so now its corresponding XS3 code, let me write down here XS3 code, it will be like 0011, right, plus 3, right? To this there will be an offset of 3 in positive direction. So 0100, 0101. For 9 in BCD, the corresponding value in XS3 is 1100. So we have all the corresponding values for BCDs what should be converted to. Okay, so now we take BCD as input. Okay, so we take these inputs variables w, x, y, z which are available to us, and by using this we need to find out the values of this XS3 code. So we take this as f4 function, f3, f2 and f1. So now if you see f4 here, f4, right, so let us write down f4 function with respect to the BCD input combinations. Let us take SOP form of representation. So I'm going to use some symbol here which represents S in the SOP, and minterms M which represents the input combinations, or minterms or product terms which represents P. Okay, so now F4 is going to be 1. Okay, when you are representing with minterms you should look for when the function is going to be 1, right? So 5, 6, 7, 8 and 9. So I'm going to write it here 5, 6, 7, 8 and 9. Okay, now if you look at this by using 4 variables, okay, here f4 is a function of 4 input variables which are w, x, y, z. By using 4 variables, the input combinations you can have is 0 to 15. So it represents 16 combinations you can have, right? Now but looking at BCD, we only have 0 to 9, which are like 10 combinations. Now what about the rest of the combinations? What happened to them? Okay, say 10 to 15. What happens is, by using 4 bits, the maximum BCD you represent is 9, and 10 to 15 you don't have a combination. So if you say you have designed a BCD to, okay, let me write down here, BCD to access 3 converter, okay, 4 outputs, 4-bit input, okay, the user will give 0 to 9 combinations to this BCD to access3 converter. The reason is the input is supposed to be BCD, so he will give only 0 to 9 combinations. He will never give 10 to 15 combinations. So in that case, do you really worry about what will be the output for this system for 10 to 15 input combinations? Because you are never going to give it as input. So that is a condition, right? So you will give only BCD as input, because it's after all BCD to access3 converter, right? So for these input combinations, by chance, what should be the output values? You really don't care, because that's not the intention of the system to be, right? So what we do is we represent this F4 with sum of M56789 plus a don't care of 10, 11, 12, 13, 14 and 15. Okay, so this is how this F4 is represented. And now question comes again, why we have to take this don't care conditions? Now the reason behind taking the don't care conditions is, if you don't consider the don't care conditions at all, you only have very few minterms, and by using this few minterms, your function equivalent expression will be bigger. If your function expression is bigger, the logic circuitry you need to build will be bigger to represent that equivalent expression. As a result, your cost of the circuit increases. So if you consider don't cares, and wherever these don't cares help you in reducing the function equivalent expression, you should be using those don't cares and build the expression for F4 and reduce the circuitry which you need to build the function. So as a result, your cost reduces, or the amount of logic circuitry you need to use reduces. So one way or the other, the power of the circuit also reduces, right? So there are a lot of advantages in considering these don't cares. The whole reason why these are don't cares is because you'll be never giving the inputs in those ranges, because after all the input should be BCD, and BCD is defined 0 to 9, okay, by using 4 bits, by the way. Okay, by using 4 bits you can define only 0 to 9, so you'll never give 10 to 15. That's the whole point. And we will see more problems, okay, based on this don't cares. And when we come to K-maps or corner maps, this makes more sense why we should be doing this. Okay, so after completing the topic, it's better to see videos on K-maps or corner maps, say, in which don't cares are considered and what is the advantage in the amount of logic reduction and so on. Thank you for watching.